When we talk about the solubility of molecular liquids in each other, there's a common saying, like dissolves like, a sort of guideline or a rule. But that question mark is significantly the objective of this little talk. What does it mean? Like dissolves like, that polar substances dissolve in polar substances. That's true of, for example, ethanol and water. Non-polar substances are miscible with non-polar substances, hexane, octane, but non-polar substances are immiscible with polar substances. Hexane and water are immiscible. But I wouldn't take this too far, and you don't have to go too far before it doesn't hold water. 1-butanol and water, miscible. It has a hydroxyl group, we would call it polar. Let me just come back to that. Propanol, miscible? Yes, it is. Octanol, 1 octanol, 8 carbon atoms in a chain, miscible? No, it's not. But you might say that this is polar, and this and water molecules are like, should dissolve. It's a bit crazy. Rules never make things should. It's what happens. Let's try to explain that. So even here, the immiscibility of octanol in water doesn't fit in with this guideline. So if we had used that, we'd have predicted wrongly. And what's more, it doesn't give us any explanatory basis for why this and water are immiscible. And if we want to go back to that, we'll go back to module 902 that I've talked about before, Prof Bob's law of miscibility, which essentially says molecules all want to mix amongst each other, be dispersed amongst each other, unless there's some energy demand, unless there's some work that has to be done. That net is too big such that it doesn't allow the molecules to do what they want to do and mix. And if we do that with ethanol and water, we have to pull the water molecules apart, we have to pull the ethanol molecules apart, and when they fit in amongst each other there's an interaction, and from the evidence that ethanol and water dissolve, we know that any energy demand, if there is a net energy demand, is not enough to overcome the natural tendency to mix. In the case of propanol, that's the same case, but in the case of octanol, just imagine that we've got these water molecules with hydrogen bonding between them, and along comes this very, very long molecule, a large chunk of which is non-polar. To be dispersed amongst these, to push into here, it has to pull apart several molecules that are interacting each other with hydrogen bonding. Lots of work needing to be done, and obviously so much work, so much energy demand that it doesn't allow the natural tendency of the molecules to mix, purely because of its size. So we've got problems with that already. I want to question this guideline a little further, talk about its shades of grey with regard to degrees of miscibility. Things are not necessarily entirely miscible or entirely immiscible. Let me start. Take example ethanol. If we add to 100 mils of water a little bit of propanol, it dissolves. If we have one layer. If we have to 100 mils of propanol a little bit of water, it dissolves. We only have one layer. So it doesn't matter what proportions these things are, they are miscible. And these things are said to be miscible in all proportions. Now, come back to butanol, the question I asked before. Do you think these are, this stuff, whose molecules are this, is soluble, miscible in water? Like dissolves like? Oh, we'd say yes. But, in fact, let's to 100 mils of water, add some 1 butanol. If I add 1 gram of butanol, shake it up, remains as 1 layer. It's miscible. Let's say total of 4 grams. It's miscible. 7 grams, 1 layer, miscible. And once I get to 8 and more grams of butanol into 100 mils of water, it is no longer totally miscible with the water, and we start to get the formation of a layer, 2 layers, one sitting on top, containing butanol. So this is just like the solubility of an ionic solid, like sodium chloride. We can add some, it's soluble, we add some, it's soluble, until we come to the point where no more can dissolve. It's a saturated solution. And exactly here we reach a saturated solution once we've gone above more than 8 grams of butanol per 100 mils. If we add more and more butanol, we increase the volume of that layer. So it's only miscible up to a point. Even more than that, in terms of shades of grey, is that this layer, at about 20 degrees, is 20% water in butanol. I'll just use C4, a C4 alcohol. The lower layer is 8% butanol, but rich in water. So there's a maximum amount that can hold, and the layers are both solutions of A and B, B and A. These are said to be partially miscible liquids. A partially miscible liquid pair. So plenty of shades of grey with regard to that. So you want to know about in between butanol and octanol, there's C5, C6, C7. If I can just use this to mean butanol, pentanol, hexanol, and heptanol, the solubilities in moles of alcohol per 100 grams of water. This one, which is the same as that, but now in moles per litre, 1.1 moles in 1 litre of water. 1 pentanol is 0.03 moles, considerably less. Hexanol, 0.006. Heptanol, 0.0008. Okay, so C3 is infinitely soluble, soluble in all proportions. The longer the hydrocarbon chain, the less soluble. This and this we'd call partially soluble. This, by the time we get to octanol, so small that we say to all intents and purposes, it's immiscible. And we can explain this, you can explain this, if you use that law of miscibility, tendency to mix, is it constrained by any energy demand? You can rationalize that quite sensibly. We can even use the same reasoning to explain the relative solubilities of substances in non-polar solvents. Like, for example, in hexane, you'd say both of these are polar, nonpolar, not like and like, insoluble. Well, in fact, methanol is immiscible in hexane, but 1-octanol is miscible in hexane. And I'm sure that you can use the same reasoning about miscibilities as we used before to explain that. The whole point of this little blurb is that there are restrictions, limitations on the validity of that statement.